All right, so we're going to talk about different ways of expressing concentration. Are you familiar with any of these?
Mole fraction, sorry, let's see, molarity for sure, but mole fraction, didn't we talk about that before?
We did. Does that help you at all?
No, I can't really remember, but I remember molarity, that's moles of solute per liter of solution.
Very good. So we have moles of solute per liter of solution. Molality is another way of expressing concentration. In this scenario, we take moles of solute per, same as molarity, but this is per kilograms of solvent. All right. Mole fraction is expressed in moles of the component of interest over total moles. All right. So remember when we were doing that gas pressure stuff before, partial pressures of gases, we said that if a solution, now solution doesn't necessarily need to be all in aqueous or liquid form, right? Solution can be a mixture of two gases. And like a balloon, here's a balloon that has air in it, which is 80% nitrogen gas, and we'll say 20% oxygen gas. All right. The mole fraction can be determined. Now this 80% and 20% oxygen gas, right, can relate to the mole fraction in that 0.8 of all of the moles of nitrogen, or 0.2 of all of the moles are all the moles of, sorry, gas, not nitrogen. But 0.8 of all the moles of gas are nitrogen, and 0.2 of all the moles of gas are oxygen here. Okay? So that's our mole fraction. And then percent by mass, percent by mass. Do you remember this at all?
Very vaguely. We did something in lab, right?
Yeah, we did. We did do that. Well, I mean, it depends on the lab class that you had. But percent by mass is referring to mass or grams of solute for every mass or grams of total solution. And that would be, so if there was 100 grams of solution and 20 grams of solute in that total grams of solution, that would be 0.2, 20 divided by 100. So you multiply it by 100 to get it to the percentage. So 0.2 times 100 would be 20%. So we want to be able to identify the molarity, the molality, and the mole fraction mass percent of any solution. And we also want to be able to identify what we call parts per million. Now, we did a lab in Chem 105. I don't know if, depending on the lab class, but sometime you might have heard of this parts per million. And I think that the easiest way to kind of think about parts per million is milligrams of solute per liter of solution, as stated here, which is the same as micrograms per milliliter. All right. Now, let me try to give you a quick explanation. It's not always quick. It sometimes takes a while. But if you can't follow this explanation, just go with the milligrams of solute per liter of solution. But if I say I have a 10 part per million solution, and let's say that means 10 milligrams of solute for every 10 milligrams for every million milligrams of solution. Okay, 10 milligrams of solute for every million milligrams of solution. Let's say my solution is in water. If I have 1,000,000 milligrams of solution, that's 1,000 grams of solution. All right, so 10 milligrams of solute for 1,000,000 or 1,000 grams of solution. 1,000 grams of solution, that is, if I have a solution that's very close to the density of water, that's 1 gram is 1 milliliter. Therefore, this can be expressed in terms of milliliters. So that's 10 milligrams of solution for every 1,000 milliliters. And then my milliliters can be converted to liters. So 10 milligrams of solute for every 1 liter of solution is the same as 10 milligrams of solute for every 1,000,000 milligrams of solution. Okay, so that's 10 parts per million. And parts per billion are just divided by 1,000, right? A million, or parts per billion divided by 1,000 gives you parts per million. Parts per million times 1,000 gives you parts per billion. Okay, and these units are generally reserved for solutions that have very low concentrations of a given compound. So, to help us kind of maneuver and learn how to understand these types of concentrations and how to identify one concentration given a different set of units, we just kind of need to organize our thoughts. Now, I provide for you this kind of table here, and we use this table to introduce our ability to organize our thoughts. Your table doesn't need to look exactly like this, but as we use, for now, you might as well. You might as well have a table that looks like this, and we'll try to write this down every time. And as we work through it, then what that's going to do is that's going to allow us to become familiar with the pertinent or the important factors to identify different concentrations in different units. So here's an example. If I have the molarity, what are the molality, mole fraction, mass percent, and parts per million concentrations? So if I have 1 molar solution of KCl and the density is 0.99 grams per milliliter, so here I have the density of the solution, here I have the solute's molar mass, here I have the solvent's molar mass. This is the molar mass of water, this is the molar mass of KCl. If I have 1 molar, what does that mean?
1 molar KCl, so that's 1 mole of KCl for every liter of solution.
Very good. So how many moles of my solute do I have?
You have 1.
That's right, I have 1 mole of my solute, and I have 1 liter of solution. All right. Now, if I know I have 1 mole of solute, can I identify the mass of that 1 mole?
You mean, oh yeah, because it's 74.55.
That's right, 74.55 grams for every 1 mole. Now, if I have 1 liter of solution, can I identify what the mass is given the density?
Let's see, that's 0.99 grams per milliliter, so grams of solution, if you had 1 liter?
That's right. Now, we could have put any value in here. I could put 2, but then I would have had to say I had 2 moles for every 2 liters. So whatever value you put in here, it's now related to these values that you're getting. So you can't change them after you start to put them down here. But once I put this in here, I can say what mass of solution I have, right? And that's going to be 0.99 grams for every liter, or milliliter, so times 1,000, 990 grams. You see that?
Oh, I didn't quite get that. How'd you get that?
Well, I wanted to know the grams of solution. I knew the volume of solution, 1 liter, and I know that there's 0.99 grams for every 1 milliliter. So if I wanted to convert that liters to milliliters, I would say there's 1,000 milliliters for every liter.
Okay, so wait.
Oh, sorry, this needs to be switched up, right?
Yeah, okay.
So we have 1 milliliter down here. That's going to cancel that out and be 0.99 grams up there. So we got grams of solution. So 0.99 times 1 times 1,000, right? And that's basically going to be 990 grams of solution.
Okay.
All right. So now I can see if I had 990 grams of solution. Of those grams of solution, 74.55 were the grams of solute, because the solution is made up of solute and solvent. So if I just take the 990 and subtract the 74.55, that's how many grams of solute I have. I can then identify 915.45 grams of solvent. All right. And from this grams of solvent, if I had 18 grams for every mole, right, I could tell you how many moles of solvent, right? So 915 divided by my 18.01, that's where we get our moles of solvent. And then I can tell you moles of solution, which is simply the combination of these two, 50.815, plus the 1 mole of my KCl. So this is the resulting total moles that I have. Now, having all these things allows us to identify molality, mole fraction, mass percent, and parts per million. Okay, so if I want to do molality first, what was molality again?
Moles of solute per, oh, I can't remember.
Moles of solute per kilogram of solvent. All right, so how many moles of solute?
I mean, on this chart?
Yeah, so we want to use the information on this chart to relate moles of solute to kilograms. Here's the kilograms right here of not solute, but solvent. All right, so this is grams of solvent, so I divide that by 1,000, 0.915. That's how many kilograms of solvent, which is the water. And I have to put above there, if I'm going for molality, moles of solute. So 1 divided by my 0.915, and that will be 1.09 or 1.1 for 2 significant figures, and that's what we're given. So that is my molality.
Okay, so mass percent, no, mole fraction.
Yeah, mole fraction is pretty straightforward. It's just moles of my material divided by what?
Total moles?
And what's the total moles here?
50.8?
It's not the 50.8, it's the...
Oh yeah, 51.8.
Very good. So 1 divided by my 51.8 will be my mole fraction, which is 0.19. 0.019, sorry, 0.019. All right, now how about my mass percent?
Mass percent, what was that again?
Mass percent is grams of solute over grams of solution.
Okay, grams of solute. Is that the 74.55?
That's right, 74.55.
And the grams of solution?
That's right, which is 990, is that right?
Okay.
So 74.55 divided by 990, 0.075, does that make sense?
Is it 7.5%?
That's right, you have to multiply it by 100, right? What we have here is the grams. What we just identified was the, not mass percent, but the mass fraction. And you multiply by 100 and it gives you the mass percent. Okay, so 7.5 is our mass percent. And then parts per million.
Oh, that was just milligrams of solute per liter of solution.
Okay, so let's just go back here and double check here, right? Parts per milligrams, micrograms of solute per milliliter of solution, or milligrams of solute per liter of solution. Very good. So milligrams of solute.
74.55 grams.
Okay, so we have to multiply that by 1,000.
Okay, yes, for milligrams.
So 74.550 milligrams of solute. Did I do that right?
1, 2, yeah, that's right.
Divided by liters of solution.
Is that just 1 liter?
That's right, 1 liter, because that's what we have defined here in our little table here. Again, if you had more solution, then all of these would be different, but the actual ratios and the actual values would be the same, right?
Yeah, I get it.
Okay, so that is my parts per million, 74,500, or 7.5 times 10 to the 4th parts per million. Okay, very good. So using this table, walking it through it, gradually helps us to kind of realize and understand the best way to approach these problems. Okay, we'll get more practice.